Okay, so we are starting with the quantum mechanical model of the atom. Sorry, we completed this earlier. I believe this is a duplication on the textbook. So the quantum numbers, right? So we are starting with the quantum numbers. There are four quantum numbers that we should know about. I want you to copy it down. Okay, just write down the
Okay.
list of it. The first one is the principal quantum number. Okay,
Okay.
the principal quantum number can be assumed orbits, similar to the Bohr's orbits. Okay,
Okay.
I said can be. Okay, they are doesn't
Can
mean
be.
that they are actually they are like orbits. Okay, they
Okay.
we can assume that they represent the orbits. Okay,
Okay.
and they are also referred as shells. Okay,
So first one is N.
yes, it is represented as an
What's it called?
principal quantum number.
Okay. Okay.
Okay,
Okay.
so principal quantum number is the number that describes size and energy of an atomic orbital. Okay,
Okay.
so it is also referred as shell, right?
Yes.
So principal quantum number represents the size and energy of the atomic orbital. And I believe we had discussed this earlier, right?
Yes.
So where I had mentioned that n is equal to 1 means the orbit or the shell which is closer to the nucleus.
Yeah. And then larger it is, the further
Yeah,
the shell.
as the number increases, it is going away from the nucleus. Important point or important observation is the gap between 1 and 2, gap between 2 and 3, gap between 3 and 4, gap between 4 and 5, and so on. What is
Slowly,
happening?
slowly decreases.
It's slowly or gradually decreasing, right? That means the energy gap is reducing between the
Yes.
consecutive numbers. Okay,
Yeah.
so Bohr was able to explain this concept. Bohr was able to explain the concept of orbits based on the hydrogen atom spectra. Okay,
Yes.
so what was happening in that? When a electron used to absorb energy, it used to jump to the higher orbital, and when it is moving back to its original orbital, it used to emit energy, and
Okay.
that energy used to be represented by the line spectra. Okay,
Okay.
okay. Uh, Now I want you to focus on this part. Bohr's success led other scientists to pursue the investigation of the line spectra in detail because there were observations that still required explanation. Okay, in 1891, Albert Michelson discovered that distinct lines in the hydrogen spectrum actually consist of many smaller lines. So that line was made up of smaller lines.
Which
Okay,
line?
uh, you remember we had shown you a picture about the emission spectra,
Oh, yes. Yes.
right? This was the emission spectra, right?
Yeah.
So these lines were made up of smaller lines.
Okay.
Okay, so it appears like a band, right? So
Okay.
assume that it is a line which is made up of finer lines. Okay,
Okay.
so Michelson discovered these smaller lines were difficult to see and were unexplained for many years. In 1915, German physicist Arnold Sommerfeld studied the hydrogen atom spectra in detail to explain the extra lines. Sommerfeld Sommerfeld proposed a secondary quantum number as a way to describe the electron energy sublevels. So it makes simple concept, right? If you are able to see smaller lines, right, in a band, correct? That means that line is made up of sublines, correct?
Okay.
Does that make sense? So imagine that this is made up of finer lines, correct?
Okay. I get it now.
So this particular line is made up of fine sublines.
So it's not solid. It's just there's small gaps and
Yes,
stuff.
yes. Okay. So
Okay.
these sublines, Sommerfeld suggested that is because of the subshells.
Okay.
Okay. So what are subshells? Orbitals of different shapes and energy as given by secondary quantum number, often referred to as SPDNF. Can you write
Yes.
down that?
Is that a type of quantum number as well?
Yes, it's a secondary quantum number.
Okay.
Okay.
Yeah, I wrote down.
Done. Okay.
Yeah.
So so is this clear why the origin of subshell was proposed?
Yes.
Okay. So now secondary quantum numbers is represented by L.
Okay.
Okay. So write down this secondary quantum number represented by L. So the number, so I want you to copy this.
Okay, I got it.
Done. Okay. So secondary quantum number is L, right? So the quantum number that describes the shape and energy of atomic orbital with whole number values from 0 to n minus 1 for each value of n. Now, what does this means? Let us understand this. So if the n number is 4, that means this is the fourth shell, correct?
Yes.
So the L numbers which are possible for n is equal to 4 is 0, 1, 2, and 3 because it says 0 to n minus 1.
Wait, could you repeat that?
Yeah. So if your principal quantum number is 4,
Okay.
then the L number for this 4, I told you what is 4? 4 represents a line
Okay.
which is made up of finer lines,
Okay.
right? So n is equal to 4 means shell number 4.
Okay.
This shell 4 is made up of 4 subshells,
Okay.
right? And those
Yes.
4 subshells are numbered as 0, 1, 2, and 3.
Okay.
Does that make sense?
Yes, I get it.
So each shell will have subshell.
And so, depending on what the value is, the certain letters are used.
Yes. So if the number is 0, that means it is S. If the number
Okay.
is 1, it is P. If the number is 2, it is D. If the number is 3, it is F. If the number is 4, it is G.
Okay.
And hypothetically, this number can go on increasing. 5, 6, 7, 8, 9, 10, and so on.
Okay.
But are they required? Not. They
No.
are not required because those, like, we don't know atoms beyond 120. Like atomic weight, sorry, atomic number 120. We don't know elements beyond that,
Okay.
right? If there is a, they are discovered, they can take the place in the periodic table, and maybe then you might need the HIJK and the other orbitals.
Okay, I get it.
Okay. So is this clear? What is the secondary quantum number?
Yes.
So we have a line. That line is made up of fine lines. The
And
line is a shell. The fine line is a subshell.
okay.
Correct?
Yes.
Any doubt?
No.
Okay. Now, so if we have n is equal to 1, right? So that means the shell number is 1. Correct?
Yes.
So the L number will be,
L number will be, if n equals 1, L would be 1,
no, L would be 0
0. Okay.
because it ranges from 0 to n minus 1. Clear?
No.
No? Okay. So if you're, check this formula, whole number values from 0 to n minus 1, correct? So you start
Yes.
n is equal to 1, correct? So your
Yes.
L will start 0, then you will say, okay, 1 minus 0 to 1 minus 1. So it is 0 to 0.
Yes.
So it means there is only one number, that is 0.
Okay.
Clear? Try
Yes.
this. If n is equal to 3, L number will be 0 to 3 minus 1. That means 0 to 2. So L number will be 0, 1, and 2.
Okay, okay.
Clear?
Okay, yeah, now I get it.
Right? So try for n is equal to 5 and tell me.
If n equals 5,
So L should be,
L should be 0, 2, 5 minus 1, so 0 to 4.
that means L is
0, 1, 2, 3, 4.
will 4, 3, yeah, yeah, 0, 1, 2, 3, and 4.
Yes.
So now if you notice, if n is 5, there are 5 subshells. Correct?
Yes.
If n is 4, you had 4 subshell. If n is 3, you have 3 subshells.
Okay.
Correct? So the principal quantum number also tells you the subshells.
Okay.
Does that make sense?
Yes.
Okay. Now, these lines which were observed were getting split when they were brought under the influence of a magnet.
Okay.
Okay. Right? So let us read this. The quantum number that describes the orientation of the atomic orbital in the space relative to the orbitals in the atom. It has a whole number value between plus L to minus L, including 0. Correct?
Okay. Yes.
So what I told you, when these lines or when that observation was put under the influence of a magnet, those smaller lines split into further smaller lines
When they're put under a magnet.
under the magnet. So the
Okay.
next quantum number is called as magnetic quantum number. Okay.
Okay.
And the value of that ranges from plus L 0 to minus L.
Okay.
Correct? Or rather,
Yes.
the easier way to is minus L 0 to plus L. That means if my n number is 4, I have L number as 0, 1, 2,
2,
and
3.
3. Correct?
Okay.
Then we cannot have minus 0 and plus 0.
Yes.
So it will be 0. Now 1. So you have minus 1,
And
0,
plus 1.
plus 1. Minus 2, minus 1, 0,
0
plus 1,
minus
plus 2.
plus 2. Yeah.
Then 3, minus 3, minus 2, minus 1, 0, plus 1, plus 2, plus 3.
Plus 3. Yeah.
Right?
Yes.
Would you like to copy this?
Yeah, I'm copying it right now.
Yeah.
Yeah, you can keep talking. I'll just keep writing.
Okay. No, I want you to copy this part. If this
Oh,
is
okay.
done, I want you to copy this. So that becomes a definition of magnetic quantum number.
It's done now.
Right? Okay. So the quantum number that describes the orientation of an atomic orbital in space relative to the other orbitals in the atom with the whole number values between plus L to plus NL minus L including 0.
Okay.
Correct?
Okay.
So can you write down this table? Table 2.
I'll take a screenshot.
Yeah. Okay. Now, so if n is equal to 1, the number of orbitals is 1.
Yeah.
If n is equal to 2, the number of subshells are 0 and 1. Correct?
N equals 2. The okay. So,
That was the reason I was asking you to copy it down. So please copy it because this concept is important.
okay.
Okay. So check this. If your n is equal to 1, your L is 0, right?
Yes.
So it is designated as 1s. ML number will be 0. Number of orbitals will be 1. Okay. If it is 2, then you have 0 and 1. If n is equal to 3,
Is
you
zero
have
one two.
0, 1, 2, and 3. If n is equal to 4, you have 0, 1, 2, and 3. Oh, I said 0. For 3, I said 0, 1. It will be 0, 1, and 2. By mistake, I said 3.
Oh, okay, okay.
Yeah. So when your n is 1, L is 0, you have only one orbital.
Yes.
When you have 2, then you have total 4 orbital.
Okay.
If n is equal to 3, you have 9 orbitals. If n is equal to 4, then you have 16 orbitals.
So or you when you just add up all the orbitals, that's when you get 16.
Yes.
Okay, okay, okay.
So, and each orbital can maximum have 2 electrons.
Okay.
So the number of electrons in each energy level is 2n square.
Okay.
So this tells you the maximum capacity.
Okay.
Doesn't mean that it needs to have those many electrons.
Okay. Like you can't have more than that. Yeah.
Yeah, it can. That's the maximum number.
Yeah.
Okay. What is the minimum number required for stability?
One.
Sorry.
One for each. One for each energy level.
No. What is the for stability? The outermost electron should, sorry, outermost shell
Should be
should
full.
have
Full should be full.
full means how many?
8.
Yes. So octet should be complete.
Okay.
So that is the minimum criteria. What we are
Okay.
discussing over here is the maximum.
So it can have more than 8 sometimes.
Yes, it can have more than 8 sometimes if there is availability of electrons.
Okay. So, like under certain circumstances, yeah, I get that.
So it is not mandatory.
Okay.
Okay, but if there are sufficient electrons, you can have more than 8.
Okay.
Okay, but what is the minimum requirement for stability?
8.
Yes. So you will see that all the inert gases, they have
Yes.
8 electrons in their outermost shell.
Okay.
Okay, except for helium, which has 2. Okay, now can
Okay.
you see over here? This you can take a screenshot.
Okay.
So check 1 and 2. 2 is split into 2 further lines. Okay, and
Yeah.
1
Three
and
is
2, they are not
three is split
overlapping
into.
over each other.
Okay.
Second and third is not overlapping each other. Correct?
Yeah.
But third and fourth, they are overlapping
They're
each other.
overlapping.
4 and 5, they are overlapping. 5 and 6, they
Yes.
are overlapping. Now it is getting more and more complex as we go higher and higher.
Okay.
So what you need to understand is that the energy gap between 4s, 3d, 4p, 4s is very, very small. So they are literally overlapping each other.
Yes.
And that is adding to some complexity that we'll learn further.
Okay.
Okay.
Okay. Okay.
So we are done with principal quantum number. We are done with secondary quantum number. We are done with magnetic quantum
Magnetic
number.
quantum.
And the third one is, sorry, the fourth one is the spin quantum number. Okay.
Spin quantum. Okay. Okay.
So spin quantum number is basically plus half and minus half. So now why? Let us understand this. Why does it make sense to have opposite spin? So can you see this is a charged particle?
Yes.
Electron is a charged particle. When it is
Yes.
rotating in this direction, or we can say it is rotating in the clockwise direction, this is the north pole.
Okay.
When it is rotating in the anti-clockwise direction, this is the south pole.
Okay.
Correct? So
Yes.
now imagine in an orbital, they are together. If the north pole and north pole, or basically they had similar spin, what would have happened?
If they are a similar spin, they would have like repel against each other.
Yes, they would have repelled against each other and they wouldn't have been in the same orbital. So if
Yes.
an electron has to be in the same orbital, it is mandatory that they should be of opposite spin.
Okay.
Correct?
Yes.
Okay. So just write down now the last part for this. That is, and now you know the reason why it needs to be plus half and minus half.
Okay.
Right? Okay. So now next is the Pauli's exclusion principle. What does it say? Pauli's exclusion principle states that in a given atom, no two electrons can have the same set of four quantum numbers.
Okay.
So if all the three quantum numbers are same, then your spin quantum number will differ.
So three of them could be the same, but not for
Yes,
all four.
yes.
So any three can be the same. Can only like certain ones be the same, and the other ones always have to be
Okay.
different.
So if they are same, right? What will
Yes.
happen is N, L, and M. If they are same, then the MS number will be different.
Okay.
Does that make sense?
Yes.
If NLR, so let us say the N number is different and L number is different, that's good enough because they are already unique now,
Yes.
right? If your N number, L number, and what is this? Magnetic quantum number. If magnetic quantum number is also same, then your magnetic spin quantum number has to be, sorry, not magnetic,
Different.
your spin quantum number has to be different.
Yes.
Clear?
Yes.
And that means an orbital can hold maximum of 2 electrons. Okay.
Okay.
Now, can you try this? 1 and 2.
Okay.
You already have the answers in front of you.
Yes. If n equals to 7, then the I is gonna range from
It's
0
not
to 6.
I, it's not I, it's L.
L is gonna range from 0 to 6
That
because
means
it's you always have to minus 1.
correct. So that means 0, 1, 2, 3, 4, 5, and 6.
Yeah, and since 6 is a large number, it's
Correct.
gonna be from 6 to 6 negative.
Yeah. So what I do is I generally start from negative number and go to the positive number. Okay.
Okay.
So can you explain why 1p, 3f, and 2d doesn't exist? Let us do this. So when we have 1s, that means your
Yes.
n number is 1, right?
Yeah.
And
Yeah.
your L number is 0. Correct? So this combination gives us 1s.
Okay.
Correct? Next
Okay.
is 1p. That means your n number is 1, your p number is what? Sorry,
P
your
number.
L number, my bad. Your L number should be 0 and 1.
Okay.
Correct?
Yes.
But we know that it stops here.
And since 0 it's with S, so it's gonna be 1S.
Yeah, so this doesn't exist. Correct?
Okay, and for 3F doesn't exist because it's gonna be 0, 1.
N is equal to 1. Sorry, n is equal to 3. L number will be 0, 1, and 2.
2.
So it will be S, P, and D. So maximum you can have is 3D. So
Yes.
3F is not possible. Correct? Maximum
Yes.
you can have is 3D.
Yes.
Okay. Then let us see next is 4F. So your N is 4. Your L number is 0, 1, 2, and 3. That is S, P, D, and F. So 4F is possible. Correct?
Okay.
Can you try 2D?
2D. Okay. So 2D is if N is 2, then it's gonna be L is gonna be 0 and 1.
Which means it is
S
Sn.
and P.
So maximum you can have is 2p.
Yes.
So 2d doesn't exist. Correct?
Okay. Yes.
Mm. So now the next is atomic structure and the periodic table. So basically, if we know the periodic table, we can uh, easily identify the electronic configuration and we can also predict what is the atomic structure.
Okay.
Okay. Progress 17 through 19, and became evident that scientists that Earth is composed of great many elements with different properties. So basically, the what you say, the crux of this information is that your periodic table, the elements are organized as per their atomic number.
Okay.
Correct?
Okay.
Okay. Mm, many electronic atoms. Bohr-Rutherford model of only limited explanation on how electrons are configured in the atom are useful for up to 20 elements. The
Yeah.
quantum mechanical model, which is four quantum numbers, not only describes all the atoms in the periodic table, but also allows us to make theoretical prediction about atoms and their chemical properties.
Okay.
Okay, so basically that is more powerful. And remember that quantum model is based on wave nature,
Okay.
correct? So three energy contribution must be considered in description of the helium atom. Once the kinetic energy of the electrons as they move about the nucleus, the potential energy of the attraction between the nucleus and the electrons, and third, the potential energy of the repulsion between the two electrons. Does this make sense?
Can you explain it?
Yeah. So if you have uh, the kinetic energy of the electrons as they move about the nucleus, so we know that nucleus has uh, protons, correct? So since it is
Yes.
helium, let us say two protons, correct?
Okay.
And in the orbit, let us assume that there are two electrons, correct?
Okay.
So the energy contribution, so how much is the energy associated with the helium? That will be decided based on the, because the electrons are moving, the kinetic energy of the electrons, correct?
Mm. So that what does that dictate?
Hello?
What is it like? What is the kinetic energy determine?
So it will help us to understand the nature of that particular atom.
Okay, and so if the number is large,
That means it is having higher energy,
and it's lower, okay, okay, I get that.
right?
All right.
So the energy contribution must be considered in the description of the helium atom, right? The
Okay.
potential energy of the attraction between the nucleus and the electron. So the proton positively charged, the electrons are negatively charged. So the first contribution is the kinetic energy, second is the potential energy between the proton and the electron, and third one
Okay.
is the potential energy of repulsion between the two electrons. Correct?
Yes.
Potential energy between the two electrons,
Okay.
right? Even though helium atom can be described in terms of quantum mechanical model, the Schrodinger wave equation cannot be solved because the repulsion between the electrons cannot be calculated exactly. This problem is called the electron correlation problem,
Okay.
correct? And because of this problem, right, it is necessary to make approximations. And most common approximation is to treat each electron as if it were moving in a field of charge that is net result of the nuclear attraction and the average repulsion of all the other electrons. The meaning of that is,
It's a cloud.
yes, but let us understand this. For example, a sodium atom has 11 electrons, 10 electrons in first and second energy subshell, 1 electron in the third subshell, correct? Now consider the single outermost electron, the force acting on it. The outermost electron is attracted to positively charged nucleus, but is also repelled by the 10 electrons in the first and
Okay.
the second energy level. The
Okay.
net effect is that the outer electron is not bound to the nucleus as tightly as it would be. if the other electrons were not present. Essence, it is screened or shielded from the nuclear charge by the repulsion of the other electrons.
So
Okay, so basically now let us understand this. So if you have a nucleus in the center, correct?
yes.
And imagine that you have a sphere surrounding the nucleus. Okay?
Oh, this is basically effective nuclear charge.
Yes.
The last electron, the
Correct.
amount of like the
Correct.
pull
Correct.
towards the center
Yes.
is only determined by how many
Correct.
electrons are in the
In the
middle
inner
things,
shell. So
initials.
what I was coming up is like imagine that there is a sphere, right? Then you have another sphere, and then you have another sphere, right? And what happens is this sphere, imagine that it is having some holes.
Yes,
This has holes, right?
yes,
So what happens is as you have more and more spheres, what happens? The last electron is away from the nucleus.
nucleus. Yes.
So the effective nuclear charge on that electron will be smaller and smaller as it moves
Okay,
away.
okay.
Okay.
Yes,
So it is not difficult in what you say when it is hydrogen because there is only one shell and there is only one electron.
one electron. So there's no effect.
But when it is having multiple, then it becomes a problem. So this is what you need
What
to
about
imagine.
What about helium? Helium only has two electrons
So
in the
helium
sphere
also it is
shell.
predictable.
So helium is also predictable. Okay,
Yes.
okay.
So that is what it said, right? Till 20, n is equal to 20, it was predictable.
Okay,
After that, it became more and more complex,
okay, I understand.
right? So the
Yeah,
wave nature helped the explanation,
yeah.
right? But don't worry about this. It doesn't go this complex, right?
Okay, okay.
So now the radial probability. What is this trying to explain? So can you see the 2s? 2s has two lines, or like two peaks,
Yes.
right? 2p has just one peak,
Okay.
correct?
Yeah. And two S
So
has two.
sorry,
Two S has two peaks.
2s has two peaks. That
Yes.
means the probability somewhere closer to the nucleus is higher. Then you have a node,
Okay.
and then what happens? You have again a
Another peak.
yeah. So let me see whether I am reading it correct. The electron is 2p orbital has its maximum closer to the nucleus. Then does the electron in the 2s orbital. You might predict
Okay.
that 2p orbital has lower energy than a 2s electron. However, notice that the small increase in the electron density that occur in the to a very near to the nucleus. This means that for a small but very significant time, the 2s electron is closer to the nucleus than the 2p electron. This effect called penetration causes an electron of 2s orbital to be attracted to the nucleus more strongly than an energy of the 2p orbital. To
Okay.
summarize, electrons in the 2s orbital possess less energy than the electrons in the 2p orbital.
Could you explain that?
So what it says is if you observe the 2p and 2s,
Yes.
it looks like the 2p has lower energy, 2s has higher energy.
Okay.
Correct?
Yeah.
Okay. But what the author is trying to say is if you observe, there is a small peak over here, which is closer to the nucleus.
Okay.
So that means that your 2s electron spends relatively more time near the nucleus. Correct? Remember
was
the remember the
says
B experiment I told you?
okay, yeah.
So that it is saying that if it is a 2s electron,
Yes.
it spends more time closer to the
Nucleus.
nucleus,
Okay.
right?
Yeah.
And less time when it is away from the nucleus.
Okay.
So although looking at the image, it appears that 2p is having higher energy, sorry, 2p is having higher energy, lower energy, and 2s has higher energy, which is not true.
Okay.
This contributes significantly to the energy,
Okay.
right? So if hypothetically I have to tell you, if we take average of two peaks of the 2s, it will come lower than the 2p.
Okay.
Does that make sense? So to summarize, electron in the 2s orbital possess less energy than the electrons in the
And the
2p
2p
orbital.
orbital.
Okay.
Okay.
Don't go into so much detail, to be honest. Like, you know what is effective nuclear charge.
Okay, so I feel like 2s means 2s is
Closer to the
like all
nucleus,
around. Or yeah. 2p is like it
away
could be
from the
a
electron. Sorry, away from the nucleus.
nucleus, yeah.
If you go 3D, further away from the nucleus.
Okay, okay, yeah. I can break it down that, yeah.
Yeah, so simple way is to remember this part.
Okay.
So check 1s closer to the nucleus, 2s further closer to the nucleus but away from 1s,
Okay.
2p away from the nucleus,
Okay.
3s further away from the nucleus. Is this clear?
Yes.
Right? Now, do you need to memorize this? Absolutely no. Okay. How we can remember this is just go to ptable.com. I don't know whether I'm sharing the. Uh, let me
No,
share.
it doesn't show.
Okay, wait. I'm just sharing the periodic table with you. Okay. So can you see
Okay.
this?
Yes,
Can
I
you
can
see
see
the
that.
can you
I
see
can
the
see the
periodic table?
I can see the
Okay.
periodic table, yeah.
Yeah. So now if you notice we have first period, right?
Yeah.
That has only two elements,
Okay.
hydrogen and helium.
Yes.
Okay. This helium should have been over here.
But didn't put it because it has a full outer shell, right?
Correct. So it has been placed along with the inert
With
gases.
the yes.
So it's an exception.
Yeah.
Correct.
Yes.
So basically, so then what I was trying to tell you is that these two are the s orbitals.
Okay.
13 to 18, these are the p orbitals.
P. Okay.
3 to 12 represent the d orbital.
E.
And this,
How many are F?
yeah, this represents, so 58 to 71
Or
represent f
F.
orbital.
Okay, that's how
I
you
have
remember
not
them.
considered La and AC.
Okay. But so besides helium, those ones are all P. Or is helium
Yes.
P as well?
No, helium is not p, helium is
Okay.
s.
S. Okay. Okay.
Okay.
Okay.
Can you write down this?
Yeah. Sure.
Yeah. So what you will say, the first two groups are s orbitals. So group 1 and 2, s orbital. Group 13 to 18, p orbital. Exception, helium. Okay.
Okay.
Group 13, sorry, group 3 to 12, d orbitals.
And bottom group.
Then the
Okay.
lanthanides and the actinides, those are f orbitals. So element after lanthanide and element after actinide. Remember that.
Okay.
Don't consider lanthanide as F. Lanthanide is D. Actinide, sorry, the lanthanum is T. Actinum is D.
Okay.
Cerium is the start of the F orbital. Thorium is
So
the start of the F orbital.
besides lanthanum and actinium, the other ones are all F.
Correct. So
Okay.
the way they are named, S block element, P block element, D block element, F block element.
Okay.
Okay.
You can continue.
Yeah. Now the next part that is important is electronic configuration.
Okay.
Okay. So for that electronic configuration, there is a concept called as Aufbau's rule.
What?
Okay.
What was the rule?
Aufbau's rule.
Elbows? Okay. Okay.
Yeah. So you can call it as mm, AUFBAU.
Okay.
Aufbau rule. So Aufbau means increasing energy.
Yes.
Okay. So if you look at the periodic table, right, the
Yes.
electrons are already arranged in increasing energy.
Okay.
Okay. So if you
Okay.
look at one, so if there is only one electron, it is 1s1, 1s1. Okay. Helium is
Yeah.
1s2.
So the numbers for the what group it is in?
No.
Oh, it's just for the actual order of the
Yes.
element. Okay. Okay.
So it is actual number like representation of the element in the periodic table. So if I
Okay.
have four electrons, so the filling would be 1, 2, 3, 4.
Okay.
Correct? So the
Okay. Okay.
electronic configuration will be 1s2 and 2s2. Are you able to get me?
One
Hello?
S2 and two S2.
So if I have four electrons, now let us understand. If I have four electrons, so I
Okay.
count 1, 2, 3, and 4.
Yeah.
Correct? So
Yes.
your first row, or sorry, your first period, right? First row
Yes.
or first period is 1s2. Your
Okay.
second period is 2s1, 2s2. So you will say 2s2. So that represents the electronic configuration of beryllium.
Okay. Okay.
On the other hand, if I say that my electron number is, let us say 9. So I count 1, 2, 3, 4, 5, 6, 7, 8, 9. Correct?
Yes.
So 9 means fluorine. So I need to know what is the electronic configuration of fluorine. So how I will go? I will start with 1s. So 1s has 1s1, 1s2. Then I'll start with 2s. So that is 2s1, 2s2.
Okay.
Correct? So from
Yes.
S, now I entered into P. Correct? Is there anything in between? In this,
Sorry, you disconnected. Could you repeat that?
so I said after the after I went into the 2s, do I have
Yes.
anything between 3 and 12 in the second row?
No.
Directly I go to the p,
Okay.
right? And I
Yeah.
have 2p, 1, 2, 3, 4, and 5. So I have
Okay.
2p, 5. Does that make sense?
Yes, that makes sense.
Okay. So how do we decide electronic configuration is? Just look at the periodic table and identify it. So let us say, oh, I missed out on something. If it is S, the number is the same as the period number.
Okay.
If it is P, the number is same as the period number.
Okay.
If it is D, the number is n minus 1. If it is F, the number is n minus 2. Can you write
Okay.
down this?
All right, done. Yeah, what was it?
I said if the electron is in the s orbital,
Yes.
then the period number is the same.
Okay.
If the electron is in the p orbital, then the period number is the same.
Okay.
If it is in the d orbital, the period number is n minus 1.
Okay.
Okay. If it is in the f orbital, the period number is n minus 2.
Okay, I
Okay.
got it.
Now, let us do an example. So, let us do vanadium. It has 23 electrons. Does that make sense?
Okay.
Because its atomic number is 23, so it has 23 electrons. And
Yes.
we need to write down the electronic configuration. So, if you look over here, this is 1s2, correct?
Yes.
This row is 2s2, 2p6.
Okay.
This row is 3s2, 3p6, correct?
Yes.
Then we enter the next row, 4s1, 4s2, correct?
Yes.
From 4s, now I am entering into D.
Yeah.
So it is 3D, correct?
-1.
So n minus 1, 4.
This is 3.
So
Okay.
it is 3. Then it is
Okay.
1, 2, and 3. So 3D3. So
Okay.
vanadium electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d3.
Okay.
Does that make sense?
Yes.
Okay. Now I want you to try iron.
For which one?
Iron, I've circled it.
Iron is going to be,
26 electrons.
wait, it's going to be uh 3D 6. 3D6.
1, 2, 3, 4, 5, 6. That's correct. But when you say it, say 4s2, 3d6.
Okay.
Okay, now what you did is you took a shortcut. So if you want to say shortcut, you can say argon and then you can say 4s2, 3d6.
Okay.
So this is a shorter version of electronic configuration, of
Okay.
representing the electronic configuration. Okay, can you try technetium?
Technetium is going to be, so first going to be 5.
Okay,
Going to be 5S. I have S1.
okay.
and then it's gonna be 4d
Why 5 is
5
1? Why didn't you say 5 is 2?
because it's in group one.
But rubidium is in the group 1. You are counting the electrons, not the elements.
Okay,
So you are
okay,
passing through this region and reaching technetium.
okay,
Okay. So
okay,
when you are reaching technetium, that means you have already passed the S. Then you enter into D.
okay.
Correct?
Then
And
it's gonna
now
be
you say
four,
1, 2, 3,
two, three,
4,
four,
5.
five. Okay.
Does that make sense?
Yes.
Okay. Now let us try rhenium. Okay, let me explain you. So you have 6s2. Is that clear?
Yes.
So you are going to reach rhenium, correct?
Yes. Yeah.
So you have to pass through 6s2. But
Okay.
if
Okay.
you notice, you have to go through the 57 to 71.
71. Yeah.
And I told you this part represents F,
Okay.
correct? Since we are
Okay.
passing through this, I will say we enter the 4F subshell.
But you also have to get past lanthanum, no?
Lanthanum. I'm coming to that. I'm grouping
Okay.
it with the 1, 2, 3, 4, and 5.
Okay.
Because they are all D, I'm grouping them together.
Okay.
Okay. Does that make sense?
Yes.
Can you try borium?
Borium. So that's gonna be 7s2,
Yeah.
5f14,
Yes.
and it's gonna be 6d5.
That's correct. Okay.
Okay.
So this is the way the electronic configuration need to be done. We'll continue this in the next class. Hope you have understood this
Yeah.
today, whatever has been done.
Okay. Okay.
Okay.
Okay. Thank you. Have a good day.
Yeah, you too. Bye.
Okay. Bye.